It's cold, it's dark, everyone, holiday stuff, parties, etc., etc. So, without further ado, Apache, Mahout, what's next? This is really exciting. This is the first time I've met people who actually have used Mahout. I've given this talk a few times now, and I feel like I'm usually doing pretty good. People at least have been passing heard of it before they came in here. Slightly different format we're going to run this time than some of my other ones. I normally like to start out kind of taking a straw poll of like what everybody's data science, data engineer, wrangler. It sounds like you guys are some real partiers and we go kind of late. So I'm going to do a kind of quick abstract at top level. We're going to run for, like I said, we're going to shoot a, oh, reminds me, start my timer because I'll just drone on forever. We're going to shoot a quick 60 minutes and then take a break. And we've got some cool demos that we're going to breeze through the top level of during this first 60 minutes, and we'll actually pop with them, get into the mechanics, and go through them a little more in depth than in the afterwards. And so that will be that. So about myself, Trevor Grant. I'm a committer on the Apache Mahout project. Recently, I joined up in June. I'm a contributor on Apache Streams Incubating, Apache Flink, Apache Zeppelin. I run the Chicago Apache Flink Meetup. Given some talks at I've been to Flink Forward. If anybody is into Flink, I recommend doing it because it's a way to get to Berlin. It's fun. I'm an open source technical evangelist for IBM. In a former life, I was a data scientist at Kroger's on-prem cloud. We did all the transactional data. Before that, I was a data scientist at a media strategy agency. And then IBM came and said, we'll pay you to go give meetups and talk and work on your favorite Apache projects. And I said, okay. And it's been really fun. And I'm on Twitter at RockinTrevo. Please follow me. You can get a hold of me on email. These slides will be up. I also run a blog of lots of little fun how-tos. All the demos you see are covered in more in-depth in blog posts. So that's about me. Oh, also MS in Applied Math and MBA, credentials, whatever. So, I don't need that slide anymore. That was kind of going back to my data science. Actually, you know what, I'm going to go with it. Data scientists versus data engineers. There's been this, when I was first running around calling myself a data scientist, there was this idea that I had, that differentiated the data scientist from the statistician. Was the data scientist still needed to have all the power, like all the knowledge of the statistician, but also could wrangle data in the distributed context, or at least use R in the Pythons, but even go further out than that, stay on that kind of edge. And that R and Python thing kind of stayed, but the world kind of split, and now there's this concept of the data engineer, for whatever reason, that we run into, where the idea that the data scientist comes up with these algorithms and models, etc., and then hands them off to the data engineer, who can write them into some sort of productionalized code. And I think that was a really great disservice to the scene, for lack of a better word, because this idea that you would have to have like two different people to like get anything done. And what's really, really exciting about the Apache Mahout project is one of the first steps of that coming back together, in that the person who writes the algorithm should also be able to write the productionalizable code in the distributed contexts. So that's kind of what I'll hope to show you as we go through this. Introduction to Mahout. So we have some people who actually used it before, have heard of it, generally familiar. Okay, Mahout was the original big data machine learning. It was machine learning on MapReduce. And that was kind of the big claim to fame. And it was a really, really good stuff. And those algorithms are still tanks and they run amazing. But what we've done since 09, starting is we've begun to pivot to using different backends, a nice Scala front end, and kind of taking a different direction. That's really what a lot of this project is going to be about. But working a lot with vector math type of things, and more of that kind of R or NumPy type of way, and integration with Apache Zeppelin. And we'll go into all this in more detail, but that's the short of it. Supposing that I encourage you all that you all want to go home and run out and play with Mahout, there are two major on-ramps if you don't want to run full compiled jars. And though that is an option if you're running Scala. Scala programs, actually, I do want to take a quick poll. Scala programmers, just a few. Java, more. Python, everybody, and then R. Okay. So, your CLI you can get into if you know, and that's just going to a command prompt the same way you start fire up Python or the Scala shell or the R shell. And that's useful. It's good for some intro stuff. Also, there is now an integration with Apache Zeppelin where you can create Mahout interpreters in your Zeppelin notebooks. And if you're not familiar with Apache Zeppelin, the short story on it is it's an Apache project. It's notebooking. It's like a notebooking web interface like Jupyter or IPython, except where those are more language oriented. Zeppelin is more big data product oriented. So you can have multiple big data products and multiple languages all in the same notebook. And you'll see kind of that in passing. But that's your on-ramp. That's really easy to get started. So some more ideas on what Mahout is now. I'm going to kind of start it by talking about what everything else is. You know, why another machine learning package? There's so many already. But they all fall short in one way or another. Starting with Spark ML MLit, you've got a bag of algorithms that are all good for demos. The people who work on it will try to convince you that it's basically sklearn on Spark. It's not. It falls really, really short. And if you ever get into Spark ML, it's very difficult to extend. So hopefully whatever your use case is very similar to whatever the demo was, because if it's not, there's not much more you can do with it. Now we have Apache System ML incubating. Can do a lot of cool things, but it requires its own scripting language. If anybody's used System ML, it has a lot of matrix algebra and R-like syntax, but you submit it you write your own script, you submit it with a Spark jar. It's somewhat tedious in that. There's some TensorFlow, and TensorFlow is a cool thing. It's open source, it's Google. It kind of can piggyback on Spark, but really wants to manage its own cluster. And so it immediately has to beg the question, like, when we have so many awesome distributed engines, do we have a machine learning package that's trying to just manage its own cluster? Why is that not being farmed out to something that's already doing a really good job of it? And then we have the sklearn and R, which are great modeling packages, very, very robust and have lots of functionality, and we can do a lot of cool things, but they're single node, and it's very troublesome to try to distribute those out. So another way for the Python folks in here to think about all this is, Spark has the data frames, which are similar to pandas in Python. Spark ML is a kind of sort of version of sklearn, and really where Mahout comes in now, the new Mahout, is very similar to NumPy, and it exposes matrix math. So that's, again, the high level, a way to kind of position these all in our head. So we'll get a little deeper into it then. Since 0.11, we came out with this vector-based math domain-specific language, which is really a type of Scala. New books come out recently, integration with notebooks that really unlock all of our visualization, leveraging all the visualization packages that happen in R and Python, we can now use with Scala and our Mahout analysis. So instead of reinventing the wheel and having to redo all these visualizations, we simply can leverage, if it exists in R or exists in Python, you can visualize Mahout with it, which is really, really exciting. We're also working, you might have read in the abstract, a new feature that we're coming out with soon is native integrations, where we use the distributed engines such as Spark or Flink to ship data around in a cluster, but then when it gets there, dump out of the JVM and run it on CPUs or GPUs for a significant speed up in computation. And we're also now starting to dabble our toes into migrating to Spark 2.0. So, just further paint the picture, and I'm realizing I think I have a couple too many painting the picture slides now, but bear with me. If we were going to have our ideal mathematical, or our ideal language for doing distributed math and data science, what are some things we would want to have? We would want it to be mathematically expressive, and I mean that in like the way R is mathematically expressive, that we can look at an algorithm or not even an algorithm, but like a matrix representation as it normally is done in academic journals or textbooks, and we can code it, and it's very one-to-one. Even if you don't understand the language, you can look at the paper, and you can look at the code and be like, okay, I get how this is this. That makes sense. Because these mathematical problems are complex enough as they are, and we don't want to incur more complexity by having to write lots and lots and lots of code to try to make, okay, this does basically this. Because then when it comes to maintaining those algorithms, or when you change a little thing, it's very, very difficult, to understand, A, what that algorithm did in the first place and where things might break. It's a problem in all programming. It's something we run into, but it's an especially big problem when you only have a small subset of people who might understand the math in the first place. So the math is very difficult to wrap your mind around. We would want it based in another language. And that, I mean, we would want to be able to leverage, we wouldn't want to have to reinvent the wheel every time we want to vectorize images or process audio. We want to take advantage of another language that already has those libraries for doing all that M processing. That would be a very important thing we would want in our ideal math language. We would want it to be distributed and yet engine independent. Spark is really exciting right now. Engines come and go. We would want our language, once we write out our algorithms, they would last as long as possible. An abstracted layer that we don't have to worry about what the back end is. I mean, we would want that for all of our code. I think that's the dream. Nobody likes porting from engine to engine to engine as time goes on, but we're calling that an ideal language, so let's shoot for the stars. And finally, an algebraic optimizer. And what I mean by that is, in the same way that you have an optimizer in any engine, SQL has query optimizers, Spark has optimizers, Flink has optimizers. They have optimizers for it lays out your job and it straightens out whatever you were doing. Well, there's certain tricks that happen in algebra. For example, if for whatever reason we said we want to take a matrix A times A transposed again, we would want our optimizer to stop us from doing silly things. Like, don't go through all the hassle of transposing the matrix twice. Just realize that's nonsense. Okay, well, so you just want the original matrix is what you're saying. And we would want a pass of that to really give us a nice little speed up. And so, without further ado, I introduced Mahout Samsara. And Mahout Samsara is what we call this Scala domain-specific language that is the new Mahout. The old Mahout being the MapReduce jobs and the Java. And we now have this Spark backend, and we expose it all through Mahout Samsara, which gives us R-like semantics for our Scala code. And so, if you look at this line there at the bottom, that, to anybody who's familiar with R, probably looks very similar to R code. Percent star percent, that's matrix. That's a matrix multiplication operator. B dot T, that's B transpose. Further, the more exciting thing is, first of all, that's all Scala, which is the exciting part. And secondly, that line above it, that's the matrix representation of stochastic principal component analysis, and we can see pretty clearly, or anybody who comes back and looks at that code, without getting into exactly what that's doing, we can see that that algorithm or formula is very clearly represented in that one line of Scala code. And keeping in mind that it is Scala code. And the benefits of it being Scala code are three big ones that jump off the page. First of all, because it's Scala code, it works with all of our current IDEs. So when you're running in IntelliJ and we import our R-like DSL, then IntelliJ picks that up and it gives us code completion and it gives us all those cool little IDE features. When we write a new language, the problem with that is we have to write the support for that language for each interpreter. We get that for free when we're just using Scala because the interpreter or the IDEs can pick that up. It gives us, as I was saying, we can leverage the other features of the host language. And we're going to have an example of where we want to vectorize images, and we don't have to rewrite all that. We just go pick another Scala package out, and boom, our images are vectorized. And finally, because it's Scala, we can compile into jars. so we can compile into Java jars. We have our math algorithms, compile them into jars that are backend independent. So we can we can make a jar with all of our math and algorithm functions and import that into, and it doesn't matter if we're running our production environment is on Spark, and then one day we move over to Flink, or whatever as we swap around our backend, we're still just importing that jars, and that math part stays the same. And that's really, really exciting when it comes to having to port these things. And we're engine agnostic. Yeah. Oh, so we're gonna go through this example in a little more depth. But what we're looking at right here is, and if it looks like it's basically the same thing on the left and the right, it's because it is with a couple of different imports. Up here at the top, we have Scala bind. This is Flink on the left. We import Flink bindings, or we import Spark bindings. And this is an ordinary least squares regression, and it is the exact same code. Copy and paste between Flink and Spark. And if anybody's worked with Flink and Spark, you will know that while they have a lot of somewhat similar paradigms and some very different paradigms, the code is normally not copy and paste. And so that's really an exciting thing too. And the algebraic optimizer, and we're gonna get into that kind of toward the end when we get into how some of this works, but for the moment, just trust me, it's a thing, and I will show it in a little bit. So, the Mahout Samsara language. These slides are gonna be online, and I would recommend people go back, but I'm not going to take everyone line by line through all of the operators. I'm gonna spin through this really quick, but what I really wanna point out as we're looking, there's a couple of things I wanna show. First of all, notice how it is very R-like, and also somewhat similar to the way NumPy would express things. We have dense vectors and sparse vectors, and we create our matrices. We have the concept of a distributed row matrix, which is our distributed matrix. In the same way an RDD is a distributed data set, we have a distributed row matrix, which is a matrix that's spread out all over the cluster. That is how but still has the same interfaces, so we can do distributed row matrix A times distributed matrix B, and it has that same interface, taking a distributed row matrix transpose. And another very exciting thing is we have slicing operators, and this is something you just really don't get in like RDDs, in a kind of sort of dirty way in data frames, but still not exactly. We can say I want columns 5 through 6. Oh, I'm sorry. Question.
Yeah. Quick question. What is? I mean, you said that it is like R. So what is the value proposition of Samsara if it's like R? Why not just use R?
R is not distributed. Is the value. The question was, what's the value proposition of Samsara? If it's like R, then the answer is R does not distribute well. As the and please do feel free to jump in. It's not lecture. This is interactive, so questions are welcome. Thank you. So yeah, we have slicing operators. A lot of things that are very, very similar. The n rows, n columns, matrix decompositions. That when you go home tonight and you start playing with Samsara, then you can go through and check out and go through the language reference. But those are the big things I want to point out on that this is very, very R-like and expressive as such. So, the big point of Mahout and the target audience that we have been that we chase are people who want to roll their own algorithms. And the idea there is, we can go, this is even more so than sklearn. Sklearn, while a very, very robust and great bag of algorithms, is still a bag of algorithms. And will take you pretty far and will hit, it's an 80-20 rule, or maybe even 90-10, where it'll get a lot of use cases, but there's sometimes you want to do some modeling that just isn't an sklearn, and you're going to have to roll it yourself. And that's usually probably a lot of times when you fall back into R. So the idea with Mahout is that you're sitting, you wake up on Monday morning, data science that you are, data science, and you're reading the Journal of Machine Learning or American Statistics Association, and you say, this is an interesting approach that is almost lockstep with a problem I have at work. I would love to implement this algorithm. And this just rolled off the presses from whatever journal, it's going to be a long time before it makes its way into Spark or even the sklearns. However, you've got a matrix implementation, and you spend the afternoon writing it out, and you've got your version of that algorithm. So that's the really exciting, and that's the value proposition of Mahout as well. And you not only have that algorithm, because you could have it in R as well, but you have it working in a distributed environment, ready to locked and loaded, ready to roll on big data. So we've got two demos in here, and these are the things that I am going to buzz through fairly quick, and then we're going to double back on after the break. But the first one, ordinary least squares. Now, before I get into how the ordinary least squares works, I want to set up a little bit of the motivation and talk about the way we normally solve a lot of machine learning algorithms, but in this case, linear regression, the stochastic gradient descent. And can I, like, most people are familiar with stochastic gradient descent and how it works? Okay, so I got some maybe. All right, so in general, the way, and this is a very dirty, oversimplified explanation, but what stochastic gradient descent does is it, given you have a set of parameters, betas, you have a set of parameters and we need to guess them, or we want to estimate them. So we make a guess, and then we calculate, the error slope, and we take a little bit, we move every parameter just a little bit in the direction that we think is going to reduce the error. Okay, and then now we check the error. Okay, now we nudge each one of the little parameters, and the idea is that this graph is really trying to show is we slowly try to walk our way down the slope to a minimum error, and that's what we're doing. We're approximating the closed form solution. And we do that because a lot of times in these machine learning algorithms, you get into a couple of situations. One, there is no closed form, or two, that there's no practical way to solve the closed form because the data set's too big and it requires holding matrices in memory, or for a number of other reasons. So stochastic gradient descent is a fun thing if you can't do a closed form. But you lose things when you do stochastic gradient descent, especially in linear regression. Specifically, if you remember just doing your old regressions, you have this concept of t values, measuring the statistical significance of each variable. And when you do stochastic gradient descent, because you never calculate your variance covariance matrix, you can still get to it, but it's different. And so we lose those things. We've got our parameter estimates, but we don't know the statistical significance of each parameter. And so that is a bummer. The motivation from Mahout then is we solve closed forms of the equations. Given the matrix, again, given the formula for solving. And in the case of linear regression is our y, our target, is our matrix of predictor variables times a vector of our betas, our parameters, and some error term. Now we can use stochastic gradient descent and just make guesses at that beta, or the way we solve is this is the solution for beta. Now that requires, you'll notice, taking a matrix times the matrix transpose and the inversion of that. And that is a lot of complicated math that has to happen in memory, and that's where it breaks down, and that's why for big data sets, even in sklearn, we're doing linear regression with stochastic gradient descent because we lose that. This is the actual form. Now, to back up and kind of go through how we implement this, we've got, we're going to make a matrix. For our X matrix, we're taking a slice, colon, that's all of our rows, 0 until 4, the first 4 columns. For Y, all rows, the fourth column, and xtx, drmx.t, times drmx, xty, and then we solve. And solving, and it returns our beta hats. Again, closed form solutions. And if you're going to go on and take the variance covariance and you want to look at that, it's the diagonal of your xtx is your variance covariance matrix and asterisk, but you're on the road. You have the things you need if you need to do that. So we have distributed linear regression.
Quick question.
Yes.
Is your approach greedy in that it needs to ingest all the data to do that operation?
So yes, all the data would be loaded into the matrix.
Yeah. Well, I mean, it's not like you
Yes.
can stream it from a very large source and just sip it, you know, at a certain rate.
True. Yes, that is accurate. So the question was, is it greedy in that it needs all the data ingested? And yes. So if you were trying to look at data streaming in, then stochastic gradient descent would not be an exactly one-to-one straightforward, but it would be a nicer fit for doing a linear regression like that. But yes. But yes, it requires everything to be in memory. The upshot, and which is why we normally don't solve it as such, because it requires so much in memory, and then so much memory to have a matrix swap go on in there. Now, once we blast that out to a distributed cluster, really we're only limited by how big our cluster is, and we've got a lot more resources than we've ever had before at our disposal, and that's again kind of the motivation. To add a bias term, so in Spark, a lot of Spark users or people who are familiar in general with map-reduce paradigm, we map things, reduce. So in Mahout we have a map block. We map blocks of the matrix. We map to blocks of the matrix. And then for this block, we iterate through, in this case, this is a way that we would add an intercept column, a column of ones to give us our intercept. This is an easier way to do it. We also have c-bind, so if we were really doing it, we just c-bind the one column. The map block, though, is useful, and I want everyone to remember that that's a thing that we do, and it's going to make more sense when we get into that. How does all this work under the hood? That we ship blocks of matrices around. That's what we map to. A little more, and again, going through now to provide some motivation why we want those reasons we would want to have those statistical significance and look at that. When we're looking at time series data, we have the problem of serial correlation. If we have serial correlation in our error terms, that is, in time one, the error term is, if our errors go, above zero, above zero, above zero, above zero, now there's zero, below zero, there's kind of some trending in the error term, that can do things like it throws off our T statistics. It throws off our estimates of statistical significance of the variables. Now, again, kind of out the window if you don't have those estimates to begin with, but once we get them, well, now we need to look at things like serial correlation. So we would want something called the Durbin-Watson test statistic. And once again, this is just me showing off again how we take this formula and in a fairly tractable way can represent it in Mahout. And that we have our error term and our lagged error term. And since we have slicing type of operations, we go from 1 until the end, 1 until end row, and then we go from 0 to end row minus 1, and that creates a lag. This presumes that our matrix is laid out in time. Row 0 is time 0. And then, so we have our numerator, E minus E lagged, squared, denominator, just E squared, numerator divided by denominator. And that's just how easy it is to implement that. A little more fancy version is once we've detected autocorrelation, we do a Cochrane-Orcutt procedure to adjust our betas for the estimates. A little more ugly, but I will say that if we go through and grok this, which we can do later, that it's still a fairly straightforward thing that has just happened here, and is easier than a similar implementation using a pure Spark or pure Flink or pure other distributed engine approach. So, okay, let's see, I'm gonna, eigenfaces, this I'm gonna, again, speed through pretty quick, and hit the highlights, and we are going to go into this one in a lot more detail after the break. So, how many people are familiar with the eigenfaces problem, though, real quick? Okay, then I'll give the background for everyone. The idea of eigenfaces is, all right, so in image recognition, image classification, we have a new image and we want to classify it as a person, or we're doing facial recognition in this particular case. Now, neural networks are all the rage, and everyone loves their neural networks. Big shortcoming of neural networks is they're very expensive to train and very costly in terms of that. And then we have the problem of, well, what happens when we add one new face to our collection? So let's say we had 10,000 people and we had one new person. Well, now we're classifying out of 10,000 with our neural networks. Now we need to classify to 10,001. We need to retrain our network. There's some kind of bootleggeries you can do to add. But one way or the other, it's going to be costly to recalculate and incorporate new people into this collection of faces. And what the eigenfaces solution is that we can come up with a set of eigenfaces and that's what these are, that's what they look like. And we can say everyone in our database, every face is a combination of these eigenfaces, and a linear combination. So now every person in our database, or every face in our database, is represented not by a full image, but by simply a linear combination of the 20 eigenfaces or the 100 eigenfaces, or however many we have. And that's really, really useful. Now, admittedly, not necessarily as accurate as neural networks, but as we're going through and we get a new face, all we need to do is decompose it into its however many eigenfaces, look at the linear combination, scan quickly through our 10,000 or however many faces we have, and say which one are you closest to. And if you're not close enough within a margin of error to any of them, then we say, oh, you must be someone new, and we just pop a 10,001 face on, and we just say you're someone new. And then we can recompute our eigenfaces, once a week or as often as needed. But this is a much more real-time solution that is useful in practice. Now then the question becomes, how do we calculate what are the eigenfaces that we should use? How do we find the linear combinations for that matrix, or how do we represent our database in linear combinations? And it turns out this is a very simple problem to solve with singular value decomposition. And because that's what singular value decomposition precisely does. That is the function of that. The question is, how do you do singular value decomposition in a distributed manner, which, lucky everyone, that's what we've got. It's one of our pre-baked algorithms. We just use a line that shows, I don't even think I have the code, it's DSSVD, whatever our image matrix is. Sorry, I'm bouncing around a lot on the things. The other real high point, though, that I'm going to touch on is this is the biggest block of code in this demo. And what we're doing, though, is we're using a Scala image package to take our 10,000 images and turn them into pixel vectors. So each image is then flattened out, each 250 by 250 image is flattened out into a vector that's 62,500 long. And so now we have vectors, and then from there it becomes, now we've got a matrix of our images where each row is an image and each column is a pixel position, and we decompose it, and then we have, so to drive this home a little more, this person, Aaron Pearsall, can be represented by this linear combination of whatevers. And yeah. So that's recognized. Now the follow-on questions you say.
So these eigenfaces
yes.
They are basically statistically independent.
No, they would be defined statistically independent.
So when you do the SVD,
yes,
you have these eigenvectors which are orthogonal to each other. Right?
Yes. Yeah, exactly. And that's really what it is. It is precisely the eigenvector problem just applied to images where we've taken our images and flattened them.
So when you try to fit a face to these eigenfaces, you basically solve a least squares problem.
That's how I decompose. Yep. And good.
So my question is, how is this different? We do it using MATLAB all the time.
Okay.
How is this just different from MATLAB?
Same thing. That how many images? At 250 by 250 an image. How many images do you think you could fit to make your calculations in MATLAB?
No, the calculations will get slower as you bring in more.
So for this, I was running on a 5-node yarn cluster, and I ran, I think the original version of it, 13,000 images, 250 by 250, took about 20 minutes. And I am unbounded by, 5-node yarn cluster for Spark I'm not even beginning to push its limits. So, I mean, it'll get slower and slower as well, but we can keep adding and adding resources. We're unbounded in, there's no point where we're gonna run out of memory and break, that's the motivation. So yeah, if you're using the MATLAB, that is another case where, yeah, it's any argument I make for R, why this Mahout versus R, definitely holds for MATLAB too. MATLAB is a tool of the people who want a lot of flexibility and power and to make their own things because they can do that. The problem with MATLAB also is you're bound to. You can get a really, really powerful machine, but you're going to be bound as how powerful a machine you can put your MATLAB on, which is the bummer. So this is now we break out distributed. So.
Question. So when we say 20 eigenfaces, anyone, let us say we are using those eigenfaces to identify someone, right?
Yep.
Like someone that comes and tries to authenticate themselves. For
Yep.
example. So are we saying, if we are saying 20, anyone that comes there to authenticate themselves will match, can be represented by these 20 faces?
Yes, asterisk. So that's a perfect segue into the Y20 faces. As you use more eigenfaces, you're going to have less error. So if I take an image out of that original database and recompose it with the 20 eigenfaces, every pixel is going to have a little bit of error on it. It's not going to be perfect, plus or minus. And so when you're trying to decide how many eigenfaces to use in the first place, what you're doing is iteratively increasing the number of eigenfaces until your average error on each reconstituted image is below some certain threshold, if that makes sense.
Okay.
Does that?
Yeah.
And then the question is, what kind of what is the error threshold that's appropriate, and how are you measuring error? And there's a lot of those questions. And the beauty of this is you're rolling your own algorithm, and you get to make that decision. It's not based on whoever wrote the algorithm, however long ago, what they decided were the things you needed to be able to tune. You're writing this thing from the ground up in a fairly quick and easy way, and you can decide, like, Euclidean distance, no, cosine distance. I used Euclidean distance in the demo. Cosine distance could be used just as easily. What you decide for your error function, also, you could do some weighting on your error, because it stands to reason on pictures of faces that pixels toward the middle are more important than pixels off to the side, because that's really just background. And you can tweak that out as much as, however you decide you want to get to do with it. And it's on you, the user.
Okay. Where do you get this data for eigenfaces?
The faces data,
Uh-huh.
also in there, and I'll go into it, but it's the labeled faces in the wild data set is a data set of about 13,000 images, all 250 by 250, that I believe they're centered with the eyes and noses in about one spot.
Where do you get that data from?
It's a public data set, and it'll be so everything I have is in actually.
Can you put the link in the meetup?
I
afterwards?
will.
Yeah.
And also I have. So we'll get into this, and I will. It has. This is the actual notebook that I'll hand out, and you can run this yourself. And so it has all the code, and you can start tweaking things. But it has very specifically the wget, how to get the actual. It has like a citation to the data set, but then like the fun thing about Zeppelin, because it's multi-language, you can run shell commands right inside. So this will, if you're running on a cluster, do all the handiwork for you. Download the data, upload it to HDFS, you're ready to rock and roll. But yeah, and we'll get into that after the break. Promise.
Yeah, the eigenfaces we saw are all slender faces. How can they be used to represent a chubby face?
So then that's a good question too. That if we have a lot of slender eigenfaces, how are they representing a chubby face? I would. Let me get this back full screen. Let's get those pictures up. Be the first thing. It's going to have two answers to that. If you have lots of chubby faces in your data set, you'll probably see some more chubby eigenfaces. This is not a great. I picked 20 just so I could have a quick 20 to show. Again, as I've read anecdotally, 80 to 120 is usually the optimal number of eigenfaces. But also, kind of going back to that pixels thing, that because some people will have the skinnier faces, even if you just have one eigenface, you'll probably get something like that that will.
Well, my point is that it will not stretch.
What's up?
My point is that there is no stretching.
No. So this is really another way to think of each one of these eigenfaces. What they are really is it's a vector of numbers where each number represents, how on 0 to 256 or 0 to 255, how filled in that grayscale pixel is. We've just reconstituted them into an image just for the sake of demonstration. But yeah.
Question, so do you have to use all of the eigenfaces? I mean, do you have to use a linear combination of all of the eigenfaces to get a particular face, or can you use only a small set?
No, the idea is you could have one of the, in your linear combination, in theory you could have 0, but the trade-off that you're looking for is you want the smallest set of eigenfaces, the smallest number of eigenfaces that will still give you the accuracy that you desire, and that's part of that iterative solving mechanism of, what is an acceptable error, what is this, what is that, what are my trade-offs in there, but that's, yeah, you want to make your set smaller.
But ideally, your optimization problem should start with all the eigenfaces, and when you converge some of those vectors on this optimized solution will be 0. This means you are not using those eigenfaces.
Yes, that would be, now you're getting into the, I want to say that. If you're doing just a straight singular value decomposition, I think, but, so, the distributed stochastic singular value decomposition was based on a paper by Nathan Halko, and that's gonna, I can't hipshot and paraphrase it, but that gets into the mechanics of precisely, it's a different way to do singular value decomposition, because going like that all the way down is implied to be too big. So it's the workaround. Note that we're using stochastics in there. We're not doing closed form, but we're approximating into it. So but that is a good point. I'm gonna go ahead then. All right. So visualizing Apache Zeppelin integration. I think at this point I've shown, okay, cool. We've got a lot of tools, just like we have in R, Python, MATLAB, for doing this math that we're used to doing. Now, as we're data sciencing around, a big thing that we like, and we've gotten probably spoiled on, we like to have, is we want to do some work, we want to do some analysis, look at a result, look at a graph, do some work, do some analysis, visualize the results, do some work, do some analysis. It's kind of that iterative thing. Now, instead of reinventing the wheel and trying to come up with a whole visualization library, we leverage Apache Zeppelin, and in short, we have a function that comes with DRMs that we'll sample the DRM to TSV. And so we have whatever our DRM is, and we want to sample like 5%. The idea there is, if it's a distributed matrix, it's too big that we don't want to try to plot all the points. We want to just take some sample of the matrix for plotting purposes. Because all the matrix has to fit in a core, and if it's distributed in the first place, yeah. So we take some sample of the matrix and it turns it into a TSV file, not a file, a TSV string, which Zeppelin has this concept called resource pools. So really what we're doing is we're taking our matrix, sampling it down to a TSV of maybe a few thousand, maybe hopefully less than 100,000 rows. We put it in this memory buffer that Zeppelin has common to all its interpreters, and then we can go in an R or Python, fish this string out, read it in like a TSV file into a data frame, into data frames, I guess, are in R and Python. We read it in, and then we just do whatever standard plotting that we have. In this case, I created a sine wave with R and Flink, with Spark and Flink, and imported them both into R. And the little red dots are the samples from the Flink, and the little blue dots are the samples from the Spark. Zeppelin also has its own Angular plotting libraries that we can utilize, which is cool. It's kind of more interactive, a little more pivot charty. Good for some things, not great for others, but it's fun that it exists. And then doing a little more exciting things, we can use scatterplot 3D. So we can start, this is, again, created a Gaussian random matrix with Mahout, and then sampled it and passed it off into R to and for visualization, which, again, the punchline here being is, if it's a plotting package that exists in R or Python, then then we can use it too. This subliminal punchline is, you can do this with anything and pass all of your things around. Apache Zeppelin's also a really cool product and deserves its own talk as such. But resource pools are a really, really handy thing for that reason. So, okay, good. Looking like we're on time. We're gonna pop the hood a little bit and talk, again, high level, how is all this working? How are we moving doing this matrix algebra in a distributed sense? And I'm gonna get into the Mahout stack, what we have, because this sets the stage for our GPU discussion too. And I don't know, can you really read that? No. Not really? Okay, then I'll talk to it very, very high level. So the top level is our application code. This is, just think of our normal Scala, we're just writing our normal Scala application and what other fun Scala things we're doing. Now we have the Scala DSL, which is that second layer, and that's our syntactic sugar, and that's where we have all of our, b.t %% b for our b matrix times b transpose, and all of that, it's not really Scala, it's that domain specific language. And that gets translated into the actual operations. And that, at that level, starts to look a lot more like Scala. And it's a function, they're methods, it's very Scala looking, and it's converting it into those actual operations, like NA matrix times ATP, and passing parameters for each function. Now in the physical DAG, this is where we start removing redundancies. It makes 3 passes over the data to check for things, to reduce things down, and that's where it goes through, wait, am I taking the same matrix and transposing it 3 times? No, we just don't need to do that. Transpose it once, or transpose it, let's get rid of the redundancies. And then we hit the physical translation layer. And at this layer is where we take, we have now a number of operations like operation A transpose times self, or A times B. And it's a set of operators, and here's where you physically implement those in Spark code, or in Flink code, or if you want to write your own backend engine, the thing that's on you then to write your own Mahout backend would be to go through that list of things and implement, okay, and whatever my engine is, how do I want to implement each of these 30 operations, or however many are in there, and in such a way you can make your own weirdo hybrid systems. Go nuts, can put true back. Then it's passed off to the actual engine, Spark, Flink, H2O. And then, once we get down to the actual nodes, okay, so now Spark and Flink are doing their things and they're pushing things around, but things are still serialized as Mahout org.apache.mahout matrix, org.apache.mahout vectors. And that's the serialization that's happening. And then when it hits the individual nodes, the actual, at the node level, then we're using Mahout in-core to do things like matrix A, in terms of matrix A transpose, because really the things that we've been serializing are just little blocks of matrices. And that's how these things are represented. And so that's where you get and that's all done with currently just regular BLAS in the JVM. And we'll get back to that in a second. Now, I'm going to, all right, optimization example. If you were writing your own, you wanted to implement in Spark a matrix A times matrix A transpose, you would probably be, if you took your first stab at it, you would want to do something along the lines of take the RDD that is matrix A and then reshuffle it around and make it into an A transpose matrix, and then multiply that times the original matrix and create some new RDD for matrix A transpose. It turns out that you can do some logical optimization on that basically looks like this. If we imagine that matrix A is now partitioned into 4 partitions, then we can save some shuffling by taking the first partition of A, and for that first block of it partitioning, it saves some shuffling and moving things around, and you get a nice little speed up of that. You're not having to ship every part of that all over the cluster. You still have to ship parts around, but you get you get a speed for that outer row product. The physical operators, there's other things that, and that's not a an exhaustive list. That's one of the many things that happen at that level. And then other things that happen, for example, when you're taking a slim matrix, i.e. a few number of columns but a long matrix, and we're trying to take like the upper triangular of that matrix. Well, that's going to be a very small matrix. So we can say, okay, well, we'll just collect that in core. We don't need that upper triangular matrix to be distributed because we know it's going to be small because this is a slim matrix. And so it has little tricks like that it does too, working deep under the hood. And so that, and there's, again, we can dive deeper in the back section, but that's where all these optimizations come in. So really, it's, if you were going to do this yourself, could you eventually? Probably. But there's lots of these little fun tricks that have already been peppered in there for you that give you all these fun speed ups that make all this stuff work and work in a fairly efficient manner.
So will it take care of if the matrix has a special structure, like for example, if it's a Toeplitz or Henkel?
If it's a what?
It's a Toeplitz or Henkel structure?
Those I don't know. It will take care of diagonal matrices. It'll take care of identity matrices. Some yes, not all. Not all is my short answer, especially without having contributed any of that code myself or been into it too terribly much.
So, which one is the required of this? Can you tell me what is Apache Flink, and then which one of those are required? You know, Flink versus Spark versus H2O
Sure.
versus Mahout. Which of these are required in my question?
That is a great question that I should have addressed much sooner, and I apologize. Apache Spark, do we all know in general Apache Spark? So, okay. Apache Flink is another distributed engine that, as Apache Spark, that shifts the paradigm, and it says, okay, all data sets are streams, and a batch of data is really just a finite stream, but we'll treat all data like streams. Whereas Spark, on the other hand, says all data is batch, and if I take a stream of data and I chop it into little blocks, it's really just mini batches. So there's two different tacks they take to the same thing, but they're both they're just distributed processing engines at the end of the day. And so does that answer that? Like, what is
Flink
Flink?
is a streaming type of concept. So
It's
everything gets computed one at a time.
It is, and yeah, that deserves a talk of its own. But for the sake of this, we'll say it's a distributed engine that takes a different approach, but even that doesn't matter for the Mahout thing. That it's a different distributed engine that can be plugged into Mahout is what Flink is for this sake. And so what you need for your cluster is, if you're going to run in distributed form, then you need either Flink or Spark. You need an engine for Mahout to run on. So Mahout really is just a set of libraries that can be run in Flink or run in Spark, if that makes sense. And then H2O is kind of this proprietary thing that we don't talk about a lot anymore. It's just
Mahout is processing engine independent. Does it run on Tez?
It does not, only because there's no bindings. So if you had Tez or you wanted to run, in theory you could write, having not known a lot about Tez, you would have to write binding. You would have to write its own set of bindings. And that's why it's also not the new Mahout is not MapReduce compliant. But no, in general, I would say it in its current state and in any kind of foreseeable future, no Tez is what I would say. Currently, the next back end, I think that we're looking at would be Spark 2.0, which raises actually perfect segue to the future work, is an interesting thing of itself. How many people have migrated from Spark 1.6 to, well, any versioning of Spark?
It's a joke.
Having done the abstraction, people on the Mahout project will tell you it is a very painful process because Spark doesn't necessarily respect this whole idea of non-API breaking changes in minor version releases. So you get that, and then when they actually have a major version like upgrade, man, everything's out the window. And so, to that respect, you can almost think of a Spark 1.6 being a totally different backend than Spark 2.0. And the benefit, or the free win for those who've been developing with Mahout is code just transfers right over. Yeah, maybe the rest of our pipeline we're going to have some pain points, but not the math parts. We just once we get the Spark 2.0 bindings in place, which is
Okay, keep going.
okay. Which is
You said you need either Spark or Flink.
yes,
So
one with
if I just, because I don't know much about Flink, but if I say, okay, if it's Spark, then it's in memory, and if it's Flink, then it's something like rstring because it kind of strings it through these cores. So is it either or is it both? You need both, and then it will work a little bit better because sometimes you string, sometimes you can.
Sure.
Some algorithms they need the memory. Sometimes you need to do the string part, like LFI or something like that.
it's either or, and I'll delve into it a little more. I'm gonna take 5 minutes real quick, and I'm just gonna hit real quick on the coming soons, and then we're gonna do our break, and we'll open up the next session with a lot of Q&A, and then start getting into demos, and we'll kind of freeform it after that, if that's all right. Okay.
I want to put one bug in your ear also. Talk about the deprecated MapReduce stuff, like what's going to happen with that.
Yes, the deprecated MapReduce
You can
stuff.
do that later, but just
Okay, I will, yeah,
Just
when
before.
we're not recording. Somebody can hang me for it. Okay. Coming soons to Mahout near you. So this is that stack that I just talked about, and here's basically what happens. Now I said when we get to the JVM, it's Mahout matrices and Mahout vectors, and we're doing Mahout math is what's happening there. And we're working on this native integration that in shorts says, okay, how big is this matrix? Or how big is this job that I'm doing? And if it's big enough, then I will dump it out of the JVM, push it in, check if GPU resources are available, and if so, push it into the GPU and let the computations happen in the GPU side. Now, I said, check how big it is, because tiny little matrices, it's not necessarily free, it's not or even cheap to dump things out of GPU and then load them into a GPU or JVM to GPU. So we want it to have a big enough job for it to do to make it worth our time. But if it is, we dump out, let the GPUs that exist optimize our calculations. We also have the CPU too. I mean, some deep learning, I think there's been a lot of buzz around GPUs doing matrix math super fast. CPUs, similar to, C++ is fast at the Java end of the day. And it's the same kind of thing. We're dumping into that for CPU calculations at lower level in this native integration. So that's a big exciting thing. And again, still letting the Spark or the Flink or whatever distributed engine handle all the shipping the data around the cluster. When it gets there, let's use the natives to optimize our computations. Also looking at consistent API and new algorithms. And this will also play into what we are hoping to do with some of the old algorithms, but we want to have this consistent API that all these algorithms, as opposed to every algorithm in a way that you might think of. Spark, R is not terrible about it, but kind of is, where every algorithm has a different implementation, a different API to it. We want to, as much as possible, kind of borrow from that sklearn paradigm where let's have fit, transform, predict, just similar, a similar interface when possible. Still kind of working out the bugs, laying out a framework, but this is coming soon. And then going through and backfilling, like I said, everything's kind of roll your own right now, and it's literally pretty much everything's roll your own. Let's throw in some commonly used things like LME for linear mixed effect models, GLM, ordinary least squares. Some of those just, daily drivers that you use a lot when you're doing old school statistics. And that is that. So with that, I am going to call for a break, do a short 10 minutes, back in seats in 10 minutes. And thanks everyone. Yeah, appreciate it. Please do come back. Like I said, there'll be more good content to follow.
Repark my car. How can I get back in?
Give me a second.
I stick a trash can in there for just a quick minute. Just because I parked the other building, the Apple's map point me to the other building. Yeah. Here's what I'll do. I'll send you
All right. Suppose then I got. But matrix X is so large it won't fit into that one. So what I can do is, so really what the matrix X is was, I've got computer 1, computer 2, computer 3, computer 4, computer 5. Really when I loaded this much of it from computer 1, this much of computer 2, 3, 4, 5. So each part of the matrix lives in the memory of its respective computer. And that's what's distributed. The matrix is distributed over 5 goes, how big they are allowed to be is a function of how big the nodes are. So let's say a possible configuration could be, let's say each one of these has, each one of these nodes has 128 gig of RAM. Then, now it's not exactly what we want to figure this over, but then in this case, it's not unreasonable, it's not less. Like, each one of these sections of the matrix is sort of 20 gig. You're not even stretching it. So at this point, then we have, let's say, 100 gig. Yeah. I think about it. What you're doing then, and this, there are things are going to change. This is matrix X. And with matrix X, I'm allowed to do matrix X like that. When you do matrix X times matrix X, I have to have X squared.
Synapse. Yeah. So that you have greater awareness. Yes. So I go, so I'm just broken. This song that I'm trying to get used to. Right. Especially when you're use an application. Yeah, so there are some specific
yes, I'm talking about R. If you can possibly put some sort of not in a R you want to start adding yeah, you can rewrite but I mean you're doing there's no that would be a huge R and man, R was doing that in the first place. Someone would have to do and since no one's out there selling it for lots of money, I'm inclined to believe there is no at the because that would be huge. If you could just R, here's R on a bus that is, and everyone says, okay, data science wars are over.
And then RSA is okay. I go through my head.
Because Python,
RSA is
better. Having worked with both,
Black Hat definitely.
Python's a little better, but even Python, there's not a clean way to do it.
Artificial
Spark is a really good way to distribute things and keeping track and handling all the data. Spark just is bad at representing the data as a matrix. So I think that's like I agree, but now you're delving into the philosophy of data science, and everyone has a different opinion. I've been a part of some of these debates, but I would agree with you. Another approach is people, well, algorithms will be designed in R, and either will be then ported to R code, like, okay, figure out exactly what we're doing, prototype in R, and then port the entire thing into Java, or whatever the other language is. Or we'll have our huge data set, and we'll just we'll either use sampling theory or like take slices and we'll just put parts of the data in and running R on like one local machine, keeping track of our results, and then we use our results together at the end, which is another approach that I also think is great, but it works. It's an approach. Or you can simply just do a sampling theory says, I've got my 99% confidence interval. The true value is somewhere. And that's statistics. We're calling it data science now. Statistics. So are you asking like where you should start?
I'm just getting feedback.
So my feeling was and always was like, look, I know my statistics and I should be able to do this in a distributed environment. And this was always kind of the way that I just kept pushing forward, and I kind of got so far along that people like me doing this. But I still think it's best because, for example, when I was at my old job, we did basically a mixed effect model, if you're familiar with mixed effect model. It's a linear regression, and you say, for example, Kroger stores exist in divisions, and then regions, and then store level, and then you also though have like, brands and individual products. You also have like categories. So you have all these like hierarchical. It's a hierarchical model, and then you also model in and say, well, stores, it's random. Sometimes it doesn't show up 500. So like blueberry yogurt, it shows 500 blueberry yogurt, and so we have like variables that count on that too. And the way we were doing it was pulling so individual slices, like, okay, so let's pull one store or one product group at a time and iterate slowly through all the stores in the database. And I'm like, that's done. We should use to run the model and run it once over all the data and not, and that would be we get smart. That's what we're doing. Yeah. Yeah. Yeah.
Yeah, but instead of just
It is, well, I mean, it's a hierarchical model. It's there's a very, they were using a very traditional, it was a mixed effects model, and it was very, very well documented. It's been around since the early 70s. Our marketing and CPG was a lot. It's tried and true. It's very, interpretable parameters, and you can go back. It's not only predicting things for you, but it's giving you insights to the parameters themselves. Like, what's the effect of advertising on a store display on product X? And then your optimization is how much money should brand X spend to promote product X with an end cap items or radio items, etc. And yeah, so that's what we're
How about you? Much of anything I've seen these meetings, so
Cure cancer. Cure cancer. I mean, that's unsolved problems. And I think most of the, I think everything has a solution. It's more of a question of how to do the solution.
And still,
Questions? Only because Sunil keeps yelling at me.
it'll be recorded, but just say what you say.
Okay.
You can't.
In general, I mean, we have, yeah.
Wait.
Okay. All right. Yeah. As far as, okay, so problems that can be solved that are solved. Everything. There's always an approach to everything. It's how much better can you make it? What's the value of making the solution better? And that can come in terms of, a lot of times can come in terms of like, well, in the case of the R, where I keep one slices of data, okay, that takes, because of that, we updated our parameter set once every 6 months, maybe a year. If you did it like this, okay, this problem will be solved out. You can do it once a week if you wanted to. do? You don't have the time cost. What's the value of that? Well, question mark. And so everything, like what's the lag? How long will you results? If you can do, if the problem current used to be, you could do it. It took 100 computers, and now to do it at the same time, we're on 10. Okay, cool. That's well, so 110 is a big jump. Is it if you put it now on 90 computers because you tweak a couple lines of code in the same amount of time? Okay, that's still pretty good improvement. So I think a lot of it is there's, or if you can improve accuracy, use accuracy 4%, great. Is it worth it? Was the time you spent looking at the problem with it? You cite it 4%. That's I think you'll always find some people hilariously case in point. You'll always find some a data science will always be able to pull some sort of answer out of their ass. Just a good answer. That's what I just did. No, but yeah, it sounds like you've got a pretty good math background too. That's awesome.
Yeah,
Awesome. See, yeah, that's then you're the person that we want to reach out and talk to because that's the developers and the people who like just kind of sort of get the escape learner in this market now. Like, man, you're not gonna do your math stuff. So, like, it's the people who actually understand it do math. Nice. Nice. Yeah.
But I've never used it.
Oh, really? Okay. Yes. So that's exactly. So that's what currently Mahout does at the local level. It does blast operations to do all that, and so that's what we're swapping out. And it's basically CUDA blast is what we're trying to swap out. So even that's like so everything in here is modular, and so even that like class level that happens in the JVM, we're trying to swap that out when possible with either native class or class or all these other ways to speed those blast operations up for sure. So exactly, and so that's what hopefully this will be, and that's what I was talking about, is that paradigm where you build in one language and then you translate it to another language, and what hopefully will be good about this, because Spark itself is a runner. In C and C++, or you get that speed up, well, you can accelerate with GPUs and and will it be as fast as a custom written C++ program to hit the GPU? No, but talk to someone who's ever programmed for GPUs, and that's an insane thing to itself, and this is all abstracted away. Your algorithm is copy pasting, now you're running at GPU speeds on a cluster environment, and that's and so to that point of what used to take, you build it and then you have to do this handoff and you have to do the C++, they make sure the C++ is really what the MATLAB said in the first place, and okay, now we can do that, we just write it once, and there's not all that handoff, so we can do we have a much faster iterative cycle, then that's an improvement to the problem. Nice. So, yeah, man, you guys might want to check this out because it sounds like you have. It sounds like that all you would need to do, and all you would need to do, would be you would have your own glass pack that would plug it at the bottom too. It seems a blush, not knowing the whole stack. The modular design of this, you could just swap out components and it would be right. Like it seems like it could shorten the steps, but probably worth looking into. I'm going to check my Slack channel. I can see if I'm getting yelled at for saying things that are blatantly inaccurate. Haven't said anything bad enough yet. Chicago. Oh, that's what I meant to say in my intro. Yeah, based out of Chicago. That's where I live. I work remote 100%. So I fly around whichever way the wind direction. Awesome. Killer. Cool. Yeah, I'm gonna grab some water and yeah, thanks very much. Awesome. I appreciate the participation. Thank you. Thank you.
No, sure. This will have so many people.
You're in Democratic campus? Yeah, that's what I'm talking
Paul is dealing with some family issues right now. He's kind of he had some and he took a job. He took a job and all this comes out
Yeah, I heard it. Is that going to be temporary or?
I think after school, what I heard is after school,
Well, there's like, all the run it in just randomly specifically yeah, and a lot of the just cost of very like way above me.
I learned about working there.
Yes. It was very interesting. Just run through our spiel of like what we do here. Oh yeah, we do this. And what they do is differently. Scrolling down. Yeah.
So was the, that was, I went to that event. So what happened? This group. I was one of
Thank you so much.
Next day,
By the way, there's another event in January. So they have like an via just for the purpose of promoting their as an address here in Dallas. So I get a lot of notifications and stuff like that. But then it's like
so, but this is a small island. I would say my background is Apache.
Well, 50% of the reason I go to the conferences is for running there's two things. When you just have an event or the conference, I'm not going to talk about it.
Still, it's about do some of the hard runs one time. And find just
yeah, there's as with anything, in theory, it sounds great.
and remember,
And so you're writing all the questions that I got for you. Questions of like, okay, well, it's benchmark, standard, which is the trick is finding something that talks about matching the audience there.
It's not like people are just coming to me with sure, I mean, they also find out so you can get a lot of this.
I know he does that in Chicago area. I think we can
Give them an understanding of how they're interested in all the things they talk about. It's not
but it would just be a matter of what's what you want to do.
I don't try and start to talk about it. That's how I work with the speakers. Well, what should we talk about?
Well, I mean, his whole career is pretty good.
Where do you feel? Key is there's lightning crash.
Sounds like an intro into somebody who's got a lot of NLP over time. Okay.
I love this. I know you use this.
this is going to solve the same problems. There's a lot to it. And the core is that I've been to a lot of bad meetups where people are yelling, and I want to make sure that whatever I have to say, and so therefore I want to make sure that because I could just talk about like what I've done for the last decade, but people like yelling about.
That's the thing, it's all down to what the description of what it is. My description.
So if that list that we have for are there any really well, I've been to buildings.
Wow, you're so nice, so thrilled.
Oh, thank you so much. I don't have business cards. IBM decided they were a non-essential business expense, which I said whatever. But
I'm so thrilled to hear you talk. I mean, my mind is blown away. It's so refreshing.
thank you. That really makes me feel good. Thank you very, very much. Awesome. Yeah, my email will be in the slide, so definitely reach out.
Great, thank you. I appreciate it. Yeah. All right. It's time to round them up.
So me and Pizza go back a long way in college. I used to join all kinds of organizations. So I used to go to
Yeah, sure. No, that's awesome.
Starvation. Like that's so good. Join clubs, free clubs there.
So Periscope's still running.
Well, then I did.
Oh, and you're IBM behind.
Well, these are
Like I said,
Yeah, I think I ate most of it. Yeah.
They want to give you some pizza.
Oh, you think I go to church?
Normally the event
And so you recharge.
They got both
It makes sense.
barely confident. Yeah. I'll
Did you go to boarding school?
like I said, I'm 100% sure they'd be very, very happy to help us.
Very rare. It's very small town here. It's very different. It's not traditional.
Okay.
I don't get resources. My sister
Too big of an organization. They can't figure it out. It's a growing branding dollars right now. Yeah, okay.
After a while,
What's up? Oh, yeah, that's and they've got, you know,
like whenever they eat some
me and Ben Brandon, they got a couple of Spark
you know, I told her I couldn't really eating because of boarding school. You have to survive.
well, we'll work it out. I'm sure there's
I think you're in college is more like boarding.
yeah.
probably ought to get started.
Yeah, no, I'm really, whenever you can think.
Maybe. You guys ready to get started again, or you want some more time? Excuse me. Want to get started?
What's that?
Okay.
All right. Live. So conclusions that I clipped off after the last one. What's next for Apache, Mahout, and you is we're gonna have questions time. You guys all already been, guys and ladies have been asking great questions. I appreciate it. We'll go through some more. We'll also go through those demos a little bit more. We can kind of delve into those. Go home and start using Mahout. It's a really, really cool project. Really, really easy on-ramps that we can talk about. Download Zeppelin, play in a notebook, join the mailing lists, get the book. The book has a lot of really, really cool things that throw out, like, it's a good thought piece, if nothing else. You go through and, like, it really gets into, like, how does matrix algebra work in a distributed context? And just as a read like that, in addition to helping you, like, get started in using Apache Mahout as a really, really good. Contribute. Apache Mahout is, there's no corporate backing. We're all volunteers. We're doing this nights and weekends. We're doing it because we love it and we really believe in the project. A couple Mondays ago, I was out in Seattle giving a talk. Guy really dug it, followed my advice, got on the mailing list, and he's helping us do documentation migration now, hopefully. So we're moving into like Jekyll. We're really looking for volunteers and people who just feel passionate about what we're doing. I was saying lots of opportunities. So please.
What's the book?
The book is Apache Mahout, Beyond MapReduce by Dimitri
Palumbo.
Palumbo. Thank you.
Yeah, he's one of the committers. I know that
Andrew
much.
Palumbo.
Yeah.
I don't know how to say Dimitri's last name.
Yeah, both of them are committers. I know Andrew is.
Dimitri is yes, or advisor.
Yeah.
Yeah. Listed as committer here, so I'm going to say committer. Credits to all the people who help out the project, and there are many, many, many more. Some fun links to follow up on: Dimitri's blog, my blog, the DSL reference, bonus material that So I think we've talked a lot, you know, as we were saying, there was a question earlier that was, what's the motivation for Apache Mahout over R, if we're all this R like DSL? Well, it's that we can do these problems that we couldn't do in single core. And it's not really an exciting thing to be like, ah, cool, I multiplied a matrix. That's not compelling. That isn't a cool thing to do. Until you do a matrix that you couldn't do on the single core. Until you take it somewhere you couldn't go with R. You find a big thing. And so to do that, you need to have a cluster. And you might be stopping and thinking like, but I don't have a 3 to 5 node yarn cluster. And what I would say is Hadoop as a service is becoming a more and more common thing. It's available on a number of competitors. IBM was my patron who flew me out here, so I will say that Bluemix is ours. Free trials, get on. I've got a blog post about setting up all this stuff, and I highly recommend you to pursue some method like that and to really get the feel. The Eigenfaces demo that we'll go through is a true big data problem. I kind of sort of got it to work on a really powerful desktop that I had, kind of, and it took about an hour, hour and a half. On a 5-node cluster, 20 minutes. So that being said, contact us. We have our user mailing list, our dev mailing list, IRC, blah, 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 blah. So that is my end spiel. And without further ado then, we do questions and demos.
So
I saw his hand first, but go ahead.
Oh, sorry, and I don't mean to derail in any way, but
No.
I'm just curious, you know, just about being an open source, you know, evangelist and working in contributor to this project. Just any general tips you have for anybody who's interested in getting into open source contributions and how to get started?
Join the mailing list is your first step on the on-ramp. Join the mailing list, download the product, and this is not just Mahout, this is pretty much anything your on-ramp is gonna be. Join the mailing list, use the product, start helping out. There's gonna be JIRA issues. Most will have either, they'll be tagged beginner issues, or you just get on and start asking like, hey, I'm new and I wanna help, what can I do? Using the product, like I said, testing releases. There's a lot of different things you can do to help. Also writing blog posts, talking, use casing, etc.
Hosting.
What's up?
Hosting.
Yeah, come up with find your project. And another thing is too about, especially when you get into the Apache projects, and open source I think to some degree in general, but the Apache especially, the Apache has this whole thing that is community over code. So it's not about like, can you write, are you the best coder in the world? It's about, it's a community, it's a club, it's a group. And you're showing up and you're hanging around, you're hanging out with the group and like, just being along. The code is a kind of a byproduct of these people hanging out who believe in whatever. In this case, in the Mahout case, it's distributed linear algebra. We think that's a really cool thing, and we all get along, we hang out, and that's the thing we put out. The streams incubating, social media, and a consistent API for accessing all the different social media APIs, and like it's a whole thing too. And so it's a group, and we know each other, and we talk all the time, and we're on the mailing list, and we see each other at the conferences. So that's kind of another thing to think of when you're getting into it. You're getting into a club. You're joining a club. So that's and go into it with that mentality. You're going in, you want to help out, you want to be a part of the club. That's what I would say.
So the database that you showed in the previous slide, the 5-node database, right?
Yes.
So does it also tell you what kind of problem they're trying to solve and what others have achieved in solving that problem?
It's a yarn cluster. It's a Hadoop cluster. It's running, it's running Big Insights, which is the IBM Hadoop distribution, and it'll have Spark on it. But it's just an empty yarn cluster,
okay.
And that's what the Hadoop as a service is. So I've got a blog post on how to slap Mahout and Zeppelin in on top of that, and then now you've got the tools at your fingertips. You could import some of the notebooks that I'll show you, the demos, and you can start running your own demos. You can write your own things, and that's what it would be. So this is really just that's the machine that will run this, the distributed big 5-node machine, and then from there it's whatever problem you want to tackle.
Benchmarks, comparisons to other systems, standard algorithms, that kind of stuff.
No. Explicitly, no. They are something we consider, or kind of chatting. Here's the problem with benchmarking between any of these systems, is everyone will always cheat the benchmark to make their product look good. If you look at any of the old Spark ML, or any of the Spark ML versus old MapReduce on algorithms, well, what are they doing? They're saying, for this small job that Spark can handle in memory, we're so much faster than MapReduce. What they're really comparing to is the old Mahout algorithms, and what they're really doing is an apples. It's not a fair comparison, because it's in-memory stuff versus MapReduce. Like, yeah, okay, that's fine until it's too big to fit in Spark, and Spark blows the doors off of itself, and that old tank MapReduce just kind of chugs along. So they were different problems. As far as any kind of benchmarking we do, we were thinking about maybe doing a little when we get the GPU accelerations, like, but then it's an apples to apples, like 5-node cluster plus CPU acceleration. How much do we speed up? And yeah, so that's why, no, in general, we don't do a lot of benchmarking, because being the mathematician, statisticians we are, we know as soon as it's garbage. We can always contrive a test to make ourselves look good. It doesn't prove anything.
Like being a client, though, you're trying to build something and you want to pick a platform. Benchmarks is something that you do. But you usually implement it yourself. You do it on one platform, you do it on another one.
Sure. And what I would say then, that as someone who is deciding what kind of road they wanted to go down for machine learning packages, I would refer you to the earlier competitive positioning slides, or you could maybe even come up with a little matrix or whatever, and like start looking, okay, what is important? Do I need a canon of pre-made algorithms, a large canon of pre-made algorithms? Do I need distributed? Do I need something that exists already? Do I need something that leverages another language so I can take advantage of all this and that? And like kind of figure out like what are the must-haves, what are the would-be nices, what are the I don't really cares, and then start looking at, okay, who fits.
Ease of construction is probably where this shines.
And that's exactly, it's that, we're distributed, because to be fair, R can do the same thing for easy construction, but we're distributed and R's not. And if you need to do some weird, spooky stuff or build your own, bleeding edge, if you're trying to stay on the razor's edge of algorithms and you want to do that sort, that's exists.
I have a couple of questions. So first, what is your preferred notebook? So you're going to stick with Zeppelin or any other notebook?
As opposed to like the Jupiters and whatever?
Yeah. Or IB, IntelliJ, or R, or whatever. Because some people are moving towards R, some people, because it's too low, it's kind of R. And
you kind of threw a bunch of different non-comparable products. You said notebooks, IDEs, and then different languages.
Yeah. You can answer it.
I guess I don't understand the question.
No, how do you interface with it?
With the notebooks?
Whether it's notebook or through R, which one would be your preferred? Because it's all about whether I have a data frame and I put it in R and I use that, or I go to Zeppelin and it's kind of the Sparky thing and I use the Spark and do that way.
So I will use, when I'm writing algorithm stuff, I'll use IntelliJ and I'll use Zeppelin. And it depends exactly what I'm doing. But I'll use Zeppelin for kind of that traditional data science-y, like iteratively, okay, I'm gonna write a couple lines, see what happens. Do this, do that. I also have Zeppelin all by IntelliJ open because, for example, anytime I write an algorithm, I don't like to do things twice. So I'll write an algorithm and then I'm throwing it in a jar and then that's where it sits and then so now I have it. And next time I need it, I'll just import it back in.
So
and I'll just have
you
it.
need those two.
You don't need them both, and that's more of like it's your preferred development lifecycle.
Because Mahout, you're saying, okay, this is kind of a platform like Storm where you can kind of start abstracting some of the stuff that you're going to do 3 times instead of trying to do it, just write it so that let Mahout handle it, and you just run your. Once you have it, then you just go to Zeppelin, and you run all your, you use it basically.
I think so, yes.
It's just a machine learning library, it's a lot of ways to use it.
Yeah.
No, because, it's coming down to, everyone has a very specific use case and they have a very specific hardware stack that needs to go against it. And you know, there are things like Spark and things, but it doesn't work for you. Then you're kind of, oh, it doesn't work for me, and you know, oh, it doesn't have the algorithm that I want. But I just am trying to do this much as multiplication, or it doesn't suit my hardware stack. Or they changed the algorithm, they changed all the stack on me. So I use Mahout because at least I have, you know, this framework to work with. You know, so that's the reason you'll choose Mahout over Spark and others, because you have no control.
Yes, kind of. One of it being the abstracted layer would be a reason, and the other being more freedom and flexibility to implement your own algorithms. Yes.
So one last question about GPUs. So is it compatible with Tesla usually, or how does it actually work with the cluster? Like if you have a Spark cluster, where does the GPU actually sit?
The GPU sits out on the nodes. So if you've got your driver. If this was Spark, this could be anything. But if this was Spark, this is your driver, and then you've got your workers, and so.
So let's say I have a 200 node cluster and I have 40 nodes.
Each node would then have a GPU.
I don't want to put 200 node of Tesla because it's a lot of money.
So yeah, and so maybe that's what you need. And that's the idea. So the idea then is you should be able to, in a comparable amount of time, take maybe, and I'm just making up numbers here, a 20 node GPU enabled cluster should be able to do it just as fast as maybe a 100 node non-accelerated cluster. That's the idea, that the data gets there and then the GPUs.
Why can't it just be like one GPU on the edge node and then just use that?
One GPU on the edge node?
Yeah.
Well, yeah, on each node you would have a GPU is the idea there.
Every node should have a GPU.